is a group that was mentored by Dr. John MacCarthy. We'll pass it on to them.
Hello everyone, my name is Whit Theo, and I'm going to be giving the first part of our presentation on the systems engineering model for the Upstate electrical energy system that my team and I developed over the past summer. This briefing is broken up into two parts, so the background and then our results and elements. Now, on to our introductions. I am Whit. I am a senior. I am a math, physics, and computer science triple major, and a partridge in a pear tree.
So I'm Bobbi Timmerman. I'm a junior, majoring in applied mathematics with physics concentration, and I call Aiken, South Carolina home.
Juan is not here. He is here in spirit. He is a computer science and applied math double major, and his home is in Charlotte, North Carolina. And our wonderful Dr. MacCarthy. In addition to my team, we also had our consultants. With our consultants, we wanted to cover all bases: academic, industrial, legislative, and nonprofit. So, the primary purpose of this model was to educate the public about the energy grid, to perform cost effectiveness trades and alternative system analyses, and also to inform policymakers about decisions around the change in the energy grid. We documented all of the data found within the model into a model description document, which includes all of the data used in our model, plus any remedial information we needed, plus all of the sources for the data that we found. So the purpose of the UEES is to provide residential, commercial, and industrial customers in upstate South Carolina with electrical power. The requirements of the UEES is to be reliable, flexible, affordable, cost-effective, and to not discriminate against industrial and consumerism. The system should also minimize negative environmental impacts. There are 5 major parts of the energy system: the generation elements, storage elements, transmission lines, substation, and distribution lines and boxes. Now, to give a brief overview of the Upstate South Carolina's electrical energy system, you can probably assume the Upstate's electrical energy system is quite expansive in size and complexity, otherwise we wouldn't be here. With a ton of moving parts and interconnected systems, as you can see, the UEES consists of 32 power lines, 18 counties, over 1.5 million individual consumers, 76 generation facilities, 3 storage facilities, thousands of miles of transmission lines, thousands of substations, tens of thousands of miles of distribution lines, and tens of thousands of distribution boxes. To combat the massive size and complexity, we decided to exclude the thousands of distribution lines, the thousands of distribution boxes, and the millions of individual customers. For the purposes of this model, we are defining the Upstate as the counties that are primarily serviced by Duke Energy Carolinas, which, as you can see, are the green areas in this red circle. And our Upstate consists of the 11 Upstate counties plus the 7 extended Franken Upstate counties. So, I know this is pretty hard to see, but this is our big kahuna model. This is what we worked on the majority of the time during our research. This is the total network model that we put into SysML. It consists of transmission lines, substations, generation facilities, and storage facilities. Now we will zoom into this little red box, and here you can see Keoe Power Plant, which is the nuclear plant, and you can trace through transmission lines and substations to get to the North Greenville tie substation. So we're getting pretty local here. And here you can see a block. A block is something that identifies the key parameters of an object.
All right, so now this is our actual data from from what we gathered about all the different technologies in the Upstate. So for our electrical energy generation element, we found about 6 different types of technologies. And within the state, there were 10 hydroelectric, 3 nuclear, 7 natural gas, 2 biofuel, 3 solar, and 1 petroleum. The picture you can see here is a picture of the Broad River Energy Center, which we have a block diagram of. And as you can see, as Whit stated, it has all of those individual key parameters for the generation element on it. Now we have the generic cost of our generation technology, so it can depend on a lot of different things: power generated, operational life, construction cost, your fixed O&M, operation and maintenance cost, and the variable O&M cost. So here we have a table that breaks down the equation and also the different parameters for that particular equation that gives us our estimated levelized cost of emissions. And as you can see in the bottom right corner, we have solar, hydro, and gas highlighted in this table. As we found out, the least expensive energy technologies are natural gas, hydroelectric, and solar. Now, specifically talking about CO2 emissions for these generation facilities, for all of them, they have some of them have output, some of them don't, but coal, petroleum, and biomass produce more than twice the CO2 as natural gas, so roughly about 1 kilogram of CO2 per kilowatt hour. And thinking on that, an average South Carolina home uses about 1.5 kilowatts per hour. And then, of course, nuclear produces no CO2, but it does produce nuclear waste, whereas wind and solar produce no CO2 and have no other pollutants. Now we have our electrical energy storage element. So 5 different types of technologies that we identified. In the Upstate, the only type that was in the Upstate were the hydroelectric pump storage, and there were 3 of them. And then we have an example of one of those pump storage facilities, which is Bad Creek. And we have a picture, and also, again, same block definition diagram for Bad Creek with those key parameters. Then we have the generic cost of storage technologies. It's the same thing. A lot of those key parameters are also in our equation. You'll note that through the table you can see that for the levelized cost of storage, the most cost-effective storage technologies are compressed air and hydrostatic. Now we move on to electrical energy transmission element. This is my baby, so very proud of it. Anyways, so there are 4 main types of transmission lines based on their voltage: 750, 500, 230, and 100. Within South Carolina, there are 0 750 kilovolt lines. And in the Upstate, there are 6 500 kilovolt, 52 230 kilovolt lines, and about 200 plus 100 kilovolt lines. And here you can see we have a picture of a transmission line and also a block diagram from one of the transmission lines. This one is a 500 kilovolt line and also showing those key parameters. Then we have the energy substation element, the other half of my baby. So again, no 750. We have 6 500 kilovolt, 35 200 kilovolt, and 100 kilovolt lines, or 400 plus 100 kilovolt lines. One thing you might know is that for substations, a 500 kilovolt substation can have transmission lines of both 200 and 100 kilovolt lines running through it, but a 100 kilovolt line cannot service anything higher. So if it's a higher voltage, it cannot run through you, which is why 200 kilovolt has 35, because some of those 500 kilovolt substations also service those as well. And then we have a substation, a picture of a substation, and again, one of those block definition diagrams. Blocks. So then we have the generic cost of transmission lines and substations. So for transmission lines, it depends on the length, the operational life, construction costs, fixed O&M, variable O&M, and retirement costs, and we estimated the levelized cost of a 230 transmission line to be about $55,000 per year per mile. With substations, a little bit different, but mostly the same. The operational life, construction replacement costs, fixed O&M costs, variable O&M, and retirement costs. And then we found the levelized cost of a 230 kilovolt station is around estimated $2.2 million a year. Then we have the distribution lines. So we are aware these are here, and we have pictures to show examples of both the distribution lines and distribution boxes, but quite frankly, there are just tens of thousands and so many we could not have been able to input them in our model or even find data analysis for. They're just too many. So now we move on to the actors in the environment. Our actors, which is consists of our customers, and those consist of industrial, residential, and commercial customers. Maintenance crews, which are delegated to the generation, transmission line, and substation. And then the environment, which consists of the power companies, the fuel providers, and the construction companies. For physical environment, we have temperature, solar irradiance, overcast/rainy days, wind speed, and wind direction. And then we have our conclusion. So our challenges were, the biggest challenges that we faced in this research project were the size and complexity of the UEES, Upstate Electrical Energy System, getting this SysML software to run and learning to use it, synchronizing our contributions to the SysML model, learning about the very wide variety of technologies, how they work. Finding data in general was one of the biggest challenges we faced, and also the volume. And then finding consistent data on power capacity factors and cost, and finding individual generic data on reliability and maintainability. And then our next steps, we would hope to develop an executable model for the cost, power, and CO2 emissions. We'd like to expand the model to all of South Carolina, perform some architecture trade-off analysis, specifically for cost and CO2, continue to share our findings, and to develop a system-level availability model